on the fact of what happens when a wave, any wave, can be a light wave, but it can also be a sound wave, hits a boundary between, say, skin and a bone, boundary between one organ and another organ. Wherever there is a boundary, wherever the medium changes from one to another, then an incoming wave will do two things. Part of it will reflect, and part of it will refract. The reflected wave, the angles of incidence will equal the angle of reflection, and the refracted wave will have an angle of refraction which is governed by Snell's law. And obviously the intensity of the incoming beam will be equal to the intensity of the refracted beam and the intensity of the reflected beam. And what we usually call these is, this is called the reflected beam, and this is called the transmitted beam, because it actually gets transmitted through the medium. So the usual way that we describe this is IR standing for the reflected beam and IT standing for the transmitted through the medium beam. Now there is a concept called acoustic impedance, which we give the letter Z, which is rho times C. Rho is the density of the medium, and C is the speed of sound through that medium. And if you're going from one medium to another, one medium that has Z1 as its acoustic impedance, and the other has Z2 as its acoustic impedance, then the ratio of the reflected beam, that's this one, the ratio of the intensity of the reflected beam to the intensity of the original beam is given by Z2 minus Z1 squared divided by Z2 plus Z1 squared. And that ratio is known as the intensity reflection coefficient. Now the difference between Z1 and Z2 for different parts of your body is actually quite small. But the difference in impedance between air and parts of your body is very large. And so you do not want any air to be in the way when you are sending a sound signal into the body and then receiving the sound signal back out of the body. And that is the reason when ultrasound is being used that the nurse or the doctor will put a gel on the surface of the skin and then put the instrument on that gel, so there is no air between the instrument and your skin, and that way the sound wave will transmit into the body, which is what you want it to do. And then all that of course is actually happening is that you put your device on somebody's skin. There will be various things under the skin, various organs that you may be trying to get some handle on, and the sound will come down. It will be transmitted, but it will also be reflected, and then it will be reflected there. And so what happens is you send out a pulse of sound. Some of it is reflected, but some of it is transmitted, and then when it hits another boundary, some of it will be transmitted, some of it will be reflected. And so what you do is you get sound, the sound pulse comes back at different times, depending on whether it's been reflected from the first or the second boundary. And that voltage pulse can be sent to an oscilloscope, where it can create a picture, a three-dimensional picture of what you're actually seeing under the skin. And if there is any irregularity there, then that should show up. Of course, you have to recognise that the further the sound pulse goes before it is reflected, the more likely it is to be attenuated, that is, to lose power. And so in this device, or in the electronics that follow it, you have to compensate for that so that this signal coming from this boundary will be stronger than this signal coming from this boundary. And in order to get a proper picture, of course, you want those strengths to be the same. So this signal coming from this boundary will need to be amplified so that it's comparable in strength to the signal coming from that boundary. The intensity of the sound at any point is given by the I0, which was the original intensity coming from the equipment, times e to the minus mu x. And mu is the linear absorption coefficient or the linear attenuation coefficient. And so the percentage of the transmission against x is going to look like this. It's an exponential decay. And rather like nuclear decay, it's a half-life. So in other words, after the half-life, you have half of what you had before. In each case, this is 1x, 2x, 3x. And in each case, the amount that you have left is half what you had before. We turn now to magnetic resonance, which used to be called nuclear magnetic resonance, but I think it probably lost the term nuclear because it gave the idea that it had something to do with nuclear power stations, and it has absolutely nothing to do with that. The nucleus in question is the nucleus in the atoms inside your body. Nuclei have a property called spin. And if there are odd numbers of protons in a nucleus, then that spin will cause the atom to behave like a tiny magnet. Hydrogen has only one proton, and therefore hydrogen, which of course is a major constituent of your body, since most of your body is made up of water, and water is H2O, and H is the hydrogen bit, that means that the water molecules, the hydrogen elements of the water molecules, act like little magnets